All right, in this video, we're going to do another application of Taylor and Maclaurin series, and that application is finding what series converge to. This might seem a little bit ubiquitous at this point, but for example, we're going to look at this series, or series similar to this. Consider an infinite series from n equals 0 to infinity of 2x to the n all over n factorial. Now at this point, basically what we're going to do in this next section is work backwards and ask ourselves, what Taylor series does this come from? Or what function does this come from? So right now, let's just write out what those few functions are that we know they're Taylor series. So for example, we have e to the x, whose Taylor series is from n equals 0 to infinity of x to the n, all over n factorial. We have 1 over 1 minus x, whose Taylor series, or power series representation centered at 0, is just x to the n from n equals 0 to infinity, and then we have our friends sine and cosine. And what our job is going to be here is basically trying to see what aspects of the series that we're handed do we see in any of these four Taylor series that we know. So for example, if we go back to the series we're handed, we can see a few attributes of this series. The first thing we see in this series, there's this n factorial. Another thing we might see is we have some number raised to the nth power. So with those two clues, we try to basically correlate this series to whatever functions Taylor series that we know. So for example, a Taylor series that has n factorial in the denominator, and where we have stuff raised to the power of n in the numerator. And this series is, of course, our exponential. Well, let me put the equal sign. And what we're going to basically do is figure out, well, I'm going to stencilify this. So everywhere there's an x, I'm going to replace by open parentheses. And I'm going to try and figure out, you know what? What needs to be in those blue parentheses that I see in the series that I'm given to go the other way to get some exponential function? So again, this is a series that we're starting with. We're able to write the series as just a 2x, quantity raised to the nth power, all over n factorial. Again, that's just a series that we're starting with. And what we saw was this is perfectly in the form of the exponential function. So really what the series converges to is e to the 2x in its series functional form. Let's do another example of this. So here's a series we're going to start with. N equals 0 to infinity of minus 1 to the n, 3 to the 2n plus 1, times x to the 2n plus 1, all over 2n plus 1 factorial. So if we just stare at this series for a while, we're going to ask ourselves, what pieces of this series look familiar to us in other Taylor series representations? So I would say in this particular series, what jumps out to us is this 2n plus 1 factorial. And what jumps out to us about this factorial is this same factorial in the denominator is in sign. Another piece that we see is this minus 1 to the n. We also note that sine also has that form. So if we start writing what sine looks like, the series for sine basically looks like a minus 1 to the nth power all over 2n plus 1 factorial. And in the numerator, we have some power or some x value being raised to the 2n plus 1. So what we need to figure out is, are there any ways that we can take our original series and combine all the leftover pieces beyond the negative 1 to the n or that 2n plus 1 factorial to combine them into those blue parentheses? So we can see that, well, if we're staring at the term 3 to the 2n plus 1 times x to the 2n plus 1, since they have the same power, we could rewrite this term as the quantity 3x to the 2n plus 1. So we can just stick a 3x into those blue parentheses, and lo and behold, this is perfectly in the form now for just sine of 3x. All right, let's do another example of this. Here's an example where we have from n equals 0 to infinity of minus 1 to the n times x to the 6n all over 2n factorial. Now we're trying to figure out what this series converges to, and because there's x values, we're asking ourselves, what function of x does this series converge to? And well, we're going to do the same exact thing. Look for the features of the series that we can see are in some of those Taylor series that we know. I would say some of the distinct features to pick up on, again, are this 2n factorial and the fact that we have this sign change, this minus 1 to the nth power. And both of these are indicative of a cosine. So if we remember what cosine looks like, we'll just write that series out flat. So it's just n equals 0 to infinity, minus 1 to the n. In cosine, we have some quantity being raised to the even power, so to raise to the 2n power, all over 2n factorial. So we see what we have in the original series we're given is that negative 1 to the n piece and that 2n factorial piece. So we just have to figure out how we can mathematically manipulate or mathematically massage that x to the 6n to get it into the form of some quantity raised to the 2n power. So this is where algebra really helps us, where we can take that x to the 6n and we could rewrite that as an x cubed all raised to the 2n power. Because again, what we're going for is some quantity being raised to the 2n power. And if we have x cubed raised to the 2n, we can multiply those powers to get x to the 6n, which were originally given. So in those blue parentheses, what we need to write is just an x cubed. So our series that we're handed, that we mathematically manipulated to get into the form of a cosine, is actually just equal to cosine of x cubed. So the key features that I want to pick up on from series that I think are important, the key feature I think to look at more than anything else is a factorial in the denominator. That generally helps guide us into what Taylor series we think this might be coming from. Because again, if we go back to the Taylor series we know, for things like the exponential, sine, 1 over 1 minus x, or cosine, each of those have different factorials. In fact, the 1 over 1 minus x doesn't even have a factorial it's getting divided by. So the fact that there is a specific factorial or there is not one could be a big indicator of what function that series may be coming from. So let's do another example. This example is going to look a bit different. For example, consider the series from n equals 0 to infinity, minus 1 to the n, 2 to the n, or actually let's get rid of 2, let's make that a 5 to the n, all over n factorial. Now what's different about this case is we're no longer just thinking about power series and what functions they're coming from in terms of x. There are no x's anywhere in this series. So if this series converges, it converges to a specific finite value. So we're going to ask ourselves the same questions. What Taylor series could this be a representative of? Or what power series does this come from? And we're going to go back to those indicators. I would say in this case, the biggest indicator we have is that factorial. We have a minus 1 to the n, but we're going to see the series that we had, those minus 1s to the n's, the sines and cosines. This is neither going to be a sine or cosine because the factorial doesn't work out that way. So if we go back and ask ourselves, what's the only series in which we have an n factorial in the denominator of those 4 Taylor series we know? Well, that is a series for the exponential, where we have some number being raised to the nth power all over n factorial, and that's equal to our friend, the exponential function of something. So in this case, we have to figure out, okay, that n factorial is taken care of in the denominator. How could I rewrite everything else in that numerator to get into those blue parentheses? So I'm going to swing that down here. So again, we have this minus 1 to the n times a 5 to the n, and what we need to do is combine this into one term to the nth power. And well, just by using some algebra, because we have 2 numbers being raised to the same power, we could multiply those numbers together and raise that product to the same power. So this is actually a minus 5 to the n. So in other words, we have our quantity being raised to the nth power for the exponential. We can take that minus 5 and put it in those blue parentheses. So that series converges to the finite number of e to the minus 5th. Or in other words, 1 over e to the 5th. That is what that series converges to. And now the point that I want to make here is before we introduced any of the power series or Taylor series, if I had just handed you this series and asked you, hey, what does this converge to? You would have had no way to know, because it's not a geometric series, integral tests, comparison tests, alternating series tests, any of those tests we had couldn't tell us what this would have converged to if it converges. So let's do another example of this. For this example, this is a series from n equals 0 to infinity, of minus 1 to the n times a 1/2 to the 2n power all over 2n plus 1 factorial. And we're asking ourselves, what series does this come from? And what is the value of this series that we're given? So we're asking ourselves, so what key features are inside of this infinite series? And the key feature, again, that I'm going to tell is this factorial. This factorial, the 1 over 2n plus 1 factorial, that's indicative of a sine function. Another, also, that minus 1 to the n, that is also indicative of a sine. Except what we have in the numerator, some number being raised to only the 2n power, that's not looking like a sine. So let's talk about it. So if we remember what sine is, it's a series from n equals 0 to infinity, minus 1 to the nth power, of some quantity being raised to the 2n plus 1, all over 2n plus 1 factorial. And if we look at the series that we're given, the series that we're given has that minus 1 to the n. It also has that 2n plus 1 factorial. But it does not have that number or a quantity being raised to the 2n plus 1. So we're going to have to work on this 1/2 to the 2n power to see how we can get it into that other form. So let's, oops, I guess I should just write, this is equal to sine of whatever's in those blue parentheses. So let's work on that 1/2 to the 2n power. So again, what we need is some quantity being raised to the 2n plus 1 power. So let's start off with this 1/2 to the 2n power. And now in math, one useful thing that we can do to increase a power by 1 is we could multiply this by a 1/2 over 1/2. What this does for us is basically say, okay, I have a 1/2 to the 2n power times a factor of 1/2 to the first. And of course, we have that division by 1/2 because we introduced that other 1/2 in the numerator. So in the numerator, we get this factor of 1/2 raised to the 2n plus 1 because we have the product of two quantities. They have the same base but different powers, so we can add the powers together and then just divided by that 1/2 in the denominator. And now we're not going to touch that 1/2 in the denominator because what we care about is that 1/2 that we got to the 2n plus 1 power in the numerator. So let's take that 1/2 to the 2n plus 1 and we can put it inside of those blue parentheses. So this looks like a 1/2 to the 2n plus 1, but because of this other factor of 1/2 in the denominator, we also have to multiply by a 1 over 1/2. Let's clean this up a bit. So we have to multiply this entire fraction by a 1 over 1/2. So inside of those blue parentheses, we can surely write the 1/2. But since we have this other factor of 1/2 here, we have a 1 over 1/2. When we're dividing by a fraction, we can reciprocate and multiply. And basically what we can do is just take this factor of 1 over 1/2 and put it out in front, which would just give us then a 2 times sine of 1/2.